Hi ladies and gentlemen, welcome to the next lesson. We're going to cover section 5.2, which is our last lesson on determinants. We're just going to cover some of the important results that we need to make sure we understand, and then we'll be done with determinants and we'll be able to move on to eigenvalues and eigenvectors. So let's just start by looking at the 5.2 summary here. A couple of really important results right out of the gate. The determinant of A transpose and A are equal to one another, and if you think about the cofactor expansions we talked about last time, this has to be true, right? This is one of these things that's kind of obviously true once we understand how to do cofactor expansions. Also, and arguably the most important result for determinants, is the determinant of a product is equal to the product of the determinants. And he follows that up with the fact that the determinant of an orthogonal matrix is equal to either 1 or -1. So this is true for permutation matrices. The determinant there is going to be either 1 or -1. So let's write down our really important result here. Determinant of A times B, that's equal to the determinant of A times the determinant of B. And we're not going to prove this result. String goes through the proof, that's fine. We're just going to take that as correct. So we're also then going to look at the idea of the elimination matrices as well as the LU decomposition. So remember, LU and Gaussian elimination, these two things are one and the same. So we'll talk a little bit about both of those. And then what we're not going to discuss is Cramer's rule. So we have no interest in Cramer's rule. It is one of these somewhat interesting results, one of the interesting applications for linear algebra, but it has no pragmatic application or purpose, and so we're not going to spend any time on that. And then finally, we'll give a brief nod to the big formula, he calls it, the big formula, but the big formula is also not useful for us, and that's because we have, remember the pitchfork? For 3 by 3, we have n factorial terms inside the pitchfork. So when we go to 4 by 4, if we were to do a 4 by 4 pitchfork, remembering that every term in the big formula, in the pitchfork, if you will, has a value from a row and a column. So it's going to have 4 values. They don't repeat rows or columns for each of the entries that's in the term there. We'll have 24 of those. That's just for a 4 by 4 matrix. If we had a 400 by 400 matrix, we would have 400 factorial terms. That's completely unrealistic. We are not going to compute anything in that manner. So it's interesting. We'll talk about it. It's important to see it, but we won't use it for computation. All right, I'm going to leave you to read this information about the diagonal matrices and the upper triangular and lower triangular matrices and their determinants, as well as the transpose and the multiplication, the product rule that we just talked about right here, as well as orthogonal matrices. And what I want to do is, instead of covering any of that, I want to just show you an example of how we can find the determinant of a triangular matrix very quickly and easily. This is one of the advantages of triangular matrices. Let me write one down. So here we have a 4 by 4 matrix, and what we want to do is calculate the determinant of this matrix. So using what we know from cofactor expansions, which column or row do you think we would want to expand on? Well, the answers are pretty straightforward. We either want to use the first column or we want to use the fourth row, because it has 3 zeros and a 1, or 3 zeros and 1 non-zero value. It's not important that it's a 1. It's important that it has 3 zeros. So it doesn't matter which one. I'm going to use the first column just because it'll make it a little bit more systematic. But remember what this is equal to. This is going to be equal to 1 then times the determinant of the 5, 6, 7, 0, 8, 9, 0, 0, 1 matrix. Well, okay. But that's equal to 1 times, and now I'm going to do cofactor expansion. So it's 1, and then it's 5 times, and I'm going to expand again along this first column. It's 5 times the determinant of the remaining matrix, which is 8, 9, 0, 1. Because the other two entries are both 0. So even though the cofactors are not 0, the determinant of what I have left over after I remove, for example, after I remove the first column and the second row, that cofactor is not equal to 0, but I'm multiplying the cofactor times the 0 that's in that spot. So that's not going to contribute. Continuing on then, I now have this is equal to the 1 multiplied times the 5 times, and now, even though I don't need to do it, this is really what I was doing when I did 2 by 2 matrices. I'm going to take 8 times the remaining value, which is 1, because that's what's left after I remove. Let me change colors. If I'm going to do, after I remove the first row and the first column, I'm left with that 1. Well, the answer then is just equal to 40. And the way I did this, I ended up by taking the product of the elements that are on the main diagonal. And that's all that's required. Remember, determinants are always applicable to square matrices and only square matrices. If the matrix is triangular, the determinant of that matrix is the product of the elements along the diagonal. That's all there is to it. And what we've really done here is kind of a simple proof for a 4 by 4 matrix, just to show how it turns out that it's the product. So that is one of the more important ideas on how we're going to actually compute the determinants, because this now fast forwards for us to A equals LU. And if we think about this, the L matrix is lower triangular, the U matrix is upper triangular. The L matrix has 1 along the main diagonals along with values down below. I don't care what those values are. The values on the diagonal here are the pivots, whatever those values happen to be. And then I have a bunch of zeros, and I have some non-zero values up here. But by combining my two big formulas, I have the determinant of A is equal to the determinant of LU, but that's equal to the determinant of L times the determinant of U. And the determinant of L is the product of the 1s. So this is just a 1. And that's going to get multiplied times the product of the diagonal elements here, which are the pivots. So that's multiplied times the product. This big capital pi symbol is product, just like the sigma symbol is for summing. The pi is for product, for multiplication. So this is really just the product, if you will, for I equals 1 to n, the UII values along the diagonal. That's it. And this is the actual means that we use for calculating determinants. As I said, really the only other time that we think about using another method is if we have a sparse matrix filled with zeros, 90% zeros, 99% zeros, lots of zeros. If we have lots of zeros, it may be faster to actually do the cofactor expansion approach. So some more conversation here on page 206, talking about the row swaps and the fact that every one of those row swaps is going to generate a change in sign. So remember, we don't often have A equals LU. We oftentimes have PA equals LU, where we've done the P matrix is permutation, or is a combination of permutation matrices. It's the product of a bunch of permutation matrices. But the point is it's either an even permutation matrix or an odd permutation matrix, and that means it has a determinant equal to 1 or negative 1. So then the determinant of A is just going to be what we discussed up here. The determinant of A is going to be what we discussed up here, except it could be positive 1 or negative 1 depending on how many row swaps we did when we were calculating the LU decomposition. So that conversation is here on page 206 with no row exchanges. All he does is give us the formula that we have up here in green. Okay. Then he's got a little bit more material here associated with determinants and the ideas of the determinants of products. And then we start in on page 207. Make sure you read through this. On page 207 is Cramer's rule. And this gets the big X from us. We are not doing Cramer's rule. Not interested in Cramer's rule. Like I said, it's a curiosity. It's interesting. It's not computationally relevant. And then there's a little bit more of this conversation about cofactors and specifically the formula that was presented last time, which has to do with the cofactor matrix, that adjugate matrix that we talked about. We don't use this to determine the inverse. Remember, our method for finding the inverse is to do Gauss-Jordan elimination. And when we take a matrix and augment it, just for review, this will be covered on the final exam, so just for review, if we take A and we augment it with the identity matrix, and then we take this and hit it with an RREF, remember A has to be square for us to have any hope of finding an inverse. This is going to give us, if A is invertible, the identity matrix and A inverse. And if it's not invertible, then we'll end up with a typical RREF where we're going to have some either row of zeros or some kind of inconsistent where we have non-zero value down here. But either way, we'll be able to tell whether it's singular or invertible, and we'll be able to tell what that inverse is if it exists. So finally then, at the very end of 5.2 is the conversation about the big formula. And really all that we want you to know about this big formula, which again, it's interesting, but outside of the 3x3 pitchfork, which you kind of use, if you don't have a computer around for determinants. Other than that, really the only important takeaway is that the growth of the number of terms in the big formula is n factorial. And because it's n factorial, we do not use it for computation. Beyond this is the conversation in section 5.3 that we're not doing. So really what we want to do is just come back and take a look at the problems for the end of section 5.2. So here are the questions. We have a matrix that we talked about last time, and what you're going to do is use MATLAB's LU command to determine what the determinant of A is. Make sure that you understand the correlation between the LU decomposition and the determinant of A. Have a little thought about what is the determinant of A times the determinant of A inverse. Think about that. That's one of the important results from the product formula that we have. And then finally, this whole concept of Gaussian or Gauss-Jordan elimination and this set of elimination matrices, whatever they might happen to be. But when we take the determinant of this matrix, which is really the U matrix, if you remember back to chapter 2 when we were doing elimination, we take the determinant of this, that's the determinant of U, but we already know that the determinant of U is equal to the determinant of A. So we want to think about why this is equal to the determinant of A. That's all. We'll see you in class. Thanks.